Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank XLR for being a part of it.
was very much interested in learning digital marketing course for a very long period of time, but I don't get a proper platform. So later for my college, I get to know about XLR and I enroll in XLR course. It was really good experience. Our course has been taken by Mayur sir, and he was very good teacher. He not only focusing on theory part, he is doing how real digital marketing works, and it was in total very good experience. I get so much of knowledge. Here they're not only focusing on study, they are also conducting different exam to test our knowledge. And as we are giving the exam, so to appreciate our work, they give certificates for the toppers, and along with the certificate they give hampers. Thank you, XLR.
Recently, I was searching for digital marketing courses online in Google, and I came across XLR, and I attended a digital marketing course which was for 15 days. My mentor Mayur helped me for attending these classes. So he is a very informative and helpful guy. In the course end, there is a exam which I topped. So I came to the XLR office in Bengaluru. This digital marketing course has helped my career and my skills to develop, and the certificate has helped my company to join. Thank you, XLR.
I came to know about this course from my college. Actually, for learning platform, this is very nice, and I learned from here ChatGPT and AI from online. Because he's teaching for me for AI generative and ChatGPT. We are using this technology in more. And after finishing the courses, I came from for collecting the certificate. I seen the classrooms and faculties. Classroom is very nice. After the completion of exam, they will give gift and certificates. Thank you, XLR, for giving these courses. I learned a lot from this. I gained the more knowledge from here. And thank you for XLR for teaching us.
Hello guys, I'm Vikram Mahajan and I'm studying in Swami Vivekananda Institute of Technology College, and I came across a training program which was mobile app development using Flutter, which was given to us by XLR Solutions. I came across this program through my college faculty, who told us about this program, that it is a very good course and you should enroll in this course. So I enrolled in this course, and initially I felt really good about this course because they started everything from a very basic point of view, that even if someone who doesn't know anything about Flutter or anything about mobile app development can also learn the same way the ones who know about it are learning. So no student was left behind and everyone was given equal attention. All the doubts throughout the course were cleared. And if we had any questions also, we were like, the trainer was also ready to stay for a longer time than it was scheduled, even for the sake of doubts. So that shows how important the students are to them. So it was a really good experience with XLR's program, and by the end of the training program, I was able to develop my own application. And through the development also, there was another point. Our sir taught us about how we can connect our own mobile phone to our laptop and write code in our laptop, and you can see the output in your phone. It was really creative and interesting for me. I felt really good about that. So in the end, I developed my own mobile application. I showed it to my mother. I showed it to my friends. I felt really good about it. So I would really suggest XLR. I would recommend it to all my friends to take courses from here, as they focus on the children, focus on the students, and they focus on what's necessary. That is, the students' doubts gets cleared and everything else. So today I came down to the XLR office to collect my certificate. So I got to know about what other courses XLR is offering. It included data analysis, data analyst, social media marketing, and full stack Java, and many more courses which were interesting, and they gave us an insight of how everything happens, and they take you through the course from the starting of the course to the end, and what next, that is placements as well. How you should be going into the interviews and how you should be approaching to companies, your resume building, and there were so many things which XLR is going to help you in, and they are ready to give you all the knowledge required, even if you are a beginner. So I really felt good about this visit, and I would really recommend XLR to everyone who's listening to this, and also to all my friends, that I had a very good experience with XLR, and I would suggest you to experience the same. Thank you.
Hello everyone, my name is Satish and I am from Swami Vivekananda Institute of Technology. I am here to share my experience about XLR program. I took part in the XLR program that was conducted in the last month about the mobile app development using Flutter. What I liked the most about this session was the trainer started from the scratch. That means even the beginner who don't know about the basics of the program, even they can learn the most from this program. It gave me hands-on experience by developing a project which was the final outcome. Thank you XLR for giving me this opportunity, and I would also recommend all my friends to take part in the XLR programs. Thank you.
Hello.
Yes, sir, we can start the class.
Hello.
Yes, sir.
Yes. Okay. So, good afternoon to all. So, let's begin the journey in this session. Let me share PPT. But yes. Yes. So we have done, yes. Let's share. Yes. So yesterday we have discussed some of the things in Dew's algorithm. So why it has been came into existence. What is the main importance? Only to prove the quantum supremacy to all. So and this oracle function, and we have discussed all these things in the circuit along with. Now, before the starting the next algorithm, that is Shor's algorithm, we were talking about. So a lot of things in the Shor's algorithm. First, I want to discuss that what is the problem Shor has identified and how he has resolved this problem by converting some other things. It was a very basic level problem, and it was hard to believe that this basic level problem is still can go as boom these things with their solution. Okay, so what they have given. So first, I can tell you that algorithm. Main thing is the algorithm. When the algorithm world is coming to our mind, then we are thinking about either very first impression that's going on CS and IT fields. That is from these fields we have to take an algorithm. And if something depth anyone can go, then he may be secondary, he may be able to think about some high level mathematics course, because in that high level mathematics course this algorithm we're discussing. Generally, I just want to highlight this point. Maybe all of you may know or not know, I don't know. I can highlight you this point that algorithm, it is not merely from the CSIT fields. So what the algorithm is, only any field we can design the steps. The algorithm are hold only steps, and that steps, sequential steps, non-sequential steps, whatever or looping or whatever is there in the algorithm. Uh, Basically, these algorithms are not solving the problem. So the very basic impression for algorithm, that algorithm solves the problem. So I want to say that this all this as my opening things. Okay, it's not that you can make these things as the ideal sentence, but yeah, it's my thinking that the algorithm are not solving the problem. Okay, the problem solution is something else beyond the algorithm. So algorithm runs on what principles, that principles or one runs on what rules, that rules solve the problem itself. Algorithm only is the way of guiding how that the program or how that your steps you are going to step in the next, how that steps is that algorithm only ensuring that steps to cover. Okay, so by what path, it is only the ensuring, but this is not the only algorithm which is solving the problem. So this is the basic of the source. That's why I'm just emphasizing these things on that. Okay, so uh, yes, so algorithm runs on the rules they are given. The rules are from mathematics. If we are going to solve a problem, then it is a mathematical problem. The rules are from the mathematics. It's a physical problem, rules are from the physics, or rules are from the chemistry, right? So whatever in which some domain or sector you are solving the problem, you are designing the algorithm. So that algorithm, to design the algorithm, you have to be guided by that rules. Right. So with this approach, I'm just moving to the this Shor's algorithm. So what was the Shor's algorithm? The Shor's algorithm is just a factor algorithm. How to factorize something and how to do this reverse, defactorize something. Okay. So that is a mathematics problem only. So on the very basic level, uh, when I entered this, I have read all these Shor's algorithm 20 years ago in my master's. Then I just read it just like it, just like the other topics. Okay, but when in the corporate sector, when some of the, you can say some of the interns, actually some of the interns came to us and asked to asked me that things. So when I was explaining them, then I realized how what is the magic behind this. So with that approach and taking that experience, I'm just in every FDP, I'm just this is my important factor. I'm just redefining these problem in a my own way. Okay, so my own way, but the taking the original things from source. Okay. So, see, the main thing is factorization problem, but anybody can think of that, just like me. That factorization, it is a left-hand game for us, right? It's a very kidding problem. The problems of the very kid level, but see, yeah, okay, very good. The problem is very kid level. Yeah, I also know that. So if this is 3 into 5, so that will give us a 15. That is very, very easy for us, right? So if we are increasing the amplitude, 15 into 150, it is also very, very easy to us. To us means we can say classical. So classical computers, these problems are nothing. 3 into 5, they can do in a fraction of seconds. 15 into 150, fraction of seconds. We are going on to increase. Why I'm talking about the increment, amplitude increment? Because this is new concept of in terms of complexity, right? There are two complexities. I think you may be aware, all of you, that the time complexity and space complexity. So we have to go in larger and see what are the time complexity is there or not, or the space complexity is there or not. If time complexity is known by algorithm steps, and all that, program running time and all that, okay, not only one factor to combining all of that, but if it is passed to the time constant, okay, then the time complexity pass, then have to see the space complexity. And whenever we want to see the space complexity, we have to look up for the hardware side. Okay. So both the complexity, it has to be passed. So suppose we are multiplying 100084, this number, to this 3001,359, this number. So this multiplication is also very, very no problem. Classical computer can do these things in a fraction of a second also. Okay. So there is no problem. There is no problem from this side. But the problem is from factorization side. If I am talking about, so now this is the forward condition. Now, if I will go onto the reverse condition, okay, onto the reverse condition. Factorization is the reverse of this multiplication, right? If we are going on the reverse condition, then if somebody is asked to factorize this one, okay, I'm just talking about the human being and the same. So whatever I'm talking about, just understand these words for both. So suppose anybody or is asked to factorize, like suppose, so this one is also very easy. So factorization, the classic 7th or 8th, the problem is they can take the long division method and to factorize, or LCM method to factorize these things, or a prime factorization method. There are three methods, at least as far as know, in the class 7th. Okay. I was not knowing until I was explaining these things, okay, to my interns and to revise. So when I revised, so only these knowledge I have collected from the experience, then from my class 7 and all that, and then I am recollected. Then I am just okay. So it is not something new. So that is, it is the recollection research for my side. So that is 150. We are going to then the different from the LCM from the um, this large factorization method. Then all that method we can do a very easily factorization. Okay, so very easily by LCM we can do the factorization is also very easy for this. So 10 into 15 we can go for that. Okay, or maybe a lot of two factors are there, here and here, like that. But this factorization will be typical when we are going for a very large number. So very large number, suppose 301125. Up to this large number, there are some exercise problems in the class, I think this 7th or 8th, when I looked up. Yes, so up to this large number, you can find the factorization. Very easy, no problem. Okay. But it will become more typical when you will be giving something to this. If we say this is 1 2 3 4 5, this is of the order of 10 to power 5. This is for the order of 10 to power 3. Okay, this is for the order of 10 to power 2. Now further moving 10 to power 10. Further moving, if we are going on the 10 to power 300, suppose 100 or 300, you can estimate what is the figure. If we are giving, if you are given like that 110011110001, and this is up to 153, like that. There's so much lengthy number up to 300 digits. 10 to the power 300 means 300 digits, like this. Okay, it will so on and continue. If you are giving to factorize this number, then I think it will take approximately, and approximately, see here in the now I'm coming to this, see here. So 3-digit numbers, it can give you 30 possible cracks, checks, and you can do the things. 6-digit number, it will have a 1000 checks. 9-digit number, 30,000 checks. So for a 100-digit number, 10 to the power 100, it will have a 10 to the power 50 possibilities. So you have to go for the 10 to the power 50 checks, right? So what the RSA technology using, that is 2048, this bit number. So that means 10 to the power 2048, right? So that almost having a 10 to the power 616 possibilities. So what it means? It means both of these is exhausting to the over limit, by the over limit of our space complexity, time as well as the space complexity. Time, I think it should take around 10 million years, 10 to 100 million years, like that. Okay, for checking this possibility. This is for the time, million years. This is for the time. Year is for the time complexity. If we are checking on the space complexity, then you can estimate for these things how much big space you required for the hardware. Okay, so this is where the classical computer fails. So with the classical computers, if we are going, it can check, this can check, this can be checked. Maybe after, maybe you have to run your program up to the 5 or 6 months or 2 months or 3 months. The servers are there, cloud computing is there. You can run the programs up to the 2 months. Okay, there are the softwares, there are simulation softwares in my materials engineering also. They are running for the 1 or 2 months on the cloud. So, but the last one, it can exhaust the universe time, whole universe time, million or billion years. Okay. And when million or billion years is required to calculate, you can estimate the space complexity behind this. Okay. So what I mean to say, as we are going in large amplitude of these numbers, then this problem is running towards the complexity ones, complexity complexes. Okay, complexity problems. So it is almost impossible to solve last two problems. Okay, almost impossible, you can say. Okay, so it is almost impossible to solve these problems from the classical computers. And this is the point where this encryption technology comes. Okay, so the security, the encryption, the RSA security numbers, so all that encryption technology are coming from this weakness of this factorization method. Okay, so we cannot factorize very easily of these things. Okay. So it will be a short or lag behind in the complexity. So here the classical computer fails. But the original one is that I was unable to explain to others that why the factor is so much typical. So also I looked out that problem, and when I looked, then this was the result I arrived. Yeah. So it was hard to believe. A factorization, it is so much easy problem. We can do the factorization. This was also my responses in the earlier days. But why the factorization has no shortcut? See, when I did my research on the net, did my things on the books, and I go through all these things and collected, then I came to know that uh, the factorization it is typical because there is no structure in how factorize behave. I will tell you example in the last next slide. Then that if there is a one pattern, one structure, that how the factorization is coming like, so it will be any rule for low factorization numbers. There will be low amplitudes, high factorization number. There is a high amplitude, or inverse rule. High amplitude numbers means low factorization. Low amplitude numbers mean high factorization. If it would be, then it will be very easy to factorize. But there is a no structure found in the factors. Then there are no formula to jump directly to the answer. It's like we know that everybody's a mathematical problem. So in the mathematical problems, or you are going to mensuration, or you are going to other mathematical problems, percentage and all that. So all that we are having a compound interest, percentage, all that we are having a very definite formulas for the to calculate, right? P into n upon something 100. Okay, so like that. So also all these things they are lacking behind in formulas. Factorization, you can also uh, you can also have to look that just remind yourself and see in your minds that yeah there is no formula for the factorization. Okay, so coincidentally I came to know these facts when I searched these things. There is no clear periodicity. So in the composite number. Composite number means what the number is factorization. That is a composite number. And also the no algebraic rule. No structure, no formula, no clear periodicity, no algebraic rule that predicts that factors. Is there any algebraic rule? Because in the reasoning, when we are going to the non-tech exams, then we have to go through the reasonings. So there is no reasoning behind this. Okay. Only the one reasoning is that uh, I will discuss these things. Only the one reasoning, as far as I was knowing up to the previous time, that just based on your LCM method and based on your memorization method, you can solve the problem. Only that's it. Now it depends how much long time you will take. So overall, this is completely unpredictable behavior from because they are lacking behind algebraic rule, periodicity, formulae, and all the regular sequential structures. So that's why we cannot guess or compute very easily. So see some examples. So I quoted some examples at here. So these are the common examples for my all the FTPs. So see, suppose if I am taking now you will be able to observe if you are taking this number, then there is a factorization 2 into 3 into 5 into 7 into 11. This. These are the small numbers. The number is this one. It is of the order of 2310. 2300 suppose. This is a round figure, na? Okay, we are taking this. So this is 2300 of the order. Second number is of same order. Third number is of same number. Fourth order. These all four are of same order. You can say it is near around 2300. Okay, not this one. Hmm. Hmm. Yes. So see, all these number are the rounding figure for all these numbers are this one, right? All these numbers are same order, but see the things. You are not able to give me a one rule or one pattern or one any algebraic something. So see here, 2, 3, 5, 7, small numbers. 11 is a mid number, mid small number. Then here 7, 3, 3, 1. Order is same, but the pattern is different. Here we are getting the factorization in small numbers. Here we are getting the factorization in 3, 3, 1. Here there is itself a prime number, so it has no factorization. Although it is of the same fact, same order. So lower one, it is also same order. Somebody will say, yeah, 3, 3, 1, you can factorize into this 1, 2, 3, 4, 5 factorization. That's why it is so small. You can go on the factorization. Okay, no problem. So you cannot find us very similar things. Maybe at here also. Okay. So you cannot find a similar things to this factorizations. Now come on to this. Order is same, right? See, it is a non-prime, it is a prime number, so it will not factorize. Prime is something that is not divisible by anything. See here, there is no pattern following. This is factor is 1087. Now this factor is 6667. If somebody will argue that, yeah, somebody may argue that here there is a one, two, three, four, five factors. Now you see here, one, two, three factors, one, two, three factors. But even the factorization is so much difference, right? And also see here. So all these are the examples that to show that justify my previous slide, right? So overall, what is the thing? The thing is that this one. There is no structure, no formula, no clear periodicity, no algebraic rule, and it is completely unpredictable behavior. So also I have interacted a lot of faculty members. So when they are explaining a Shor's algorithm, they are just explaining that we are explaining that it has no factorization. Factorization is very typical. Okay. But the students are not getting this point. And from just like me also. So just like that, that concept is transferring 10 years to 15 years until unless she will or he will get himself involved in this. So that's why I cleared this thing. Now it has no pattern, no structure, no clear periodicity. That's why the factorization is impossible problem for the computation method. Now, so classically, I have found also this is also I have found in the literature that uh, there are four methods for the factorization is still there, which is involved somewhere faster speeds. So one is the trial division method. Everybody knows this. Okay. Second one is parallel Pollard row method. In the Pollard row method, what was happening that suppose you have to choose, like suppose there are, I'm just stop thinking about data sorting. Okay. Suppose you want to choose the right key. Suppose all these are the key. One, two, three, four, five. All these are the keys. You have to choose the right key. Then maybe possible you can choose this one, this one, this one, this one, all the six. And maybe possible you can first choose this, then choose this. Or you can make a rule. First choose this one, then choose this one. If not, then choose middle one. If not, then choose left one and then right one, like that. Okay. So maybe possible it every rule, as the rule is bypassed, so you will bypass the possibilities. And this is your luck. You are finding a possibility in a one round from this and this rule, or from middle rule, or from there and rule, like that. Okay. So there may be several rules. So among that several rules, what Pollard found, he has done the research, but Pollard found if we are going or forming a rule like that, there are several keys, suppose they are distributed throughout the ways. And Pollard said that if we want to choose one key, so there is a one method that what you can go by row, symbol row. So let me take a different color. Symbol row means you can choose by this. You can go like this and this. Okay, you can go like this and this. So he has found there is no logic behind that, but he has found empirical. So that is called empirical basis. Empirical basis means you are doing experiment, you are observing, doing experiment, you are observing, then you make the rule. That is called empirical rules. Okay, so he's found by this geometry, you are going like this and this. By geometry, you are having a good possibility of finding the solution first. So somewhat it has adapted to the community. So this is called Pollard row. So it is good, but for the until the medium size numbers. Okay. So the medium size number, you can found the possibility in 1 or 2 rounds or 3 rounds only. Okay. But not suitable for the RSS size numbers. So in the RSS size number, still this method fails. Now, for the next methods, so what are the things? There are two more methods. So now there is a quadratic sieve method. Okay. So in the quadratic sieve method, it is also same thing, and but its limit is also towards the 100 to 120 digit numbers. Okay. So this is my literature. I would suggest that it may be possible there may be a more method of factorization, but what I found in all my literature and all my research, that these are the four methods until this. This is up to the 120 digit numbers, but it can, if we adopt and feed this rule in the classical algorithm, it will also take a very large time, almost 1 month. So now the next method is number field sieves. This method is also good and has now fastest known method for the classical algorithm. Okay, so somebody may argue for that argues this is the fastest method. Okay, so in the classic for the classical ones, but still it can take several months, but it can do. Yeah, it can do. It is not impossible. Just like the algorithm we were saying that it is impossible to calculate from the number in a whole universe. But still, it is lacking behind in the RSS. That is, if we are going to the 10 to power 2000 numbers. Okay. So for these digits, or you can say 2000 digit numbers around 2000 digit number, although it is a 2048, you can say near about 2000 digit numbers, then still it will fail. Okay. So all the methods has its own capacity, has its own speed, and but all these speed are still failing in the classical computation. Okay. So overall, this weakness uh, is very much advantages for our security. So in all the security systems, whether it is a banking sector or whether it is a finance sector, whether it is a something is encrypted way of things. So all these things are running on this weakness. Okay. So that is, it is very typical to factorize. So what the companies are doing, okay, in all of the sectors, my acquaintances are there, and they were telling me like this. So what they are doing, so they are just choosing a random 2000 digit number, suppose. They are choosing a random 2000 digit number, and this random 10 to power 2000 digit number, that means 10 to power 2000, you can say the value. Okay. And this 2000 digit number, they randomly, what they are saying randomly we are doing 1000, suppose 1200 digit number multiplied by then 1200 digit number. Randomly they are taking 115353996 like this. Okay. So like that. So randomly they are taking, they are multiplying, and they are making a one code for this. They are making a one code for that. Then now you can say multiplication is very easy. So we can multiply. And until unless we know, we don't know that this is the factors, we cannot reverse this thing. So multiplication we can do for the computation. It can multiply and it can give you a key. So this is a one type of key in RS encryption. Okay. And to break this key, it is almost impossible. Almost impossible. Okay. Until unless you are not knowing these factors. So if you are knowing these factors are called the keys. These are the two keys. If you are knowing these factors, then you can do. Otherwise, you can't. Okay. So all our modern encryption technology are running on these facts, or this weakness of our math. Okay. So that's why the factorization is so much typical. Okay. Now coming to the main topic of this FDP, that shows what the show did. I hope so that I am able to make you clear behind the soul behind this factorization problem. Okay. So I have found very rare faculties, some of from IIC. One faculty I found from the not Chennai, that is Kanpur. Yeah. They have discussed a lot in this, but rather than I have found very less that somebody has know that what the factorization and why the factorization is typical. Overall, so now coming to the mm, next slide. Yes, shores. Now, yes, now come to the shore side. Shore has made the algorithm. We are calling this as a Shor's algorithm. Everybody is knowing, I think, because in FDP, I think some of the beginners are there. Beginners are there, then they also knows. They are also, I think, they are searching the quantum computation in the YouTube also, so they can know the Shor's algorithm. And I think all my colleagues and teachers and faculties, if they are you are teaching this course, then you know the Shor's. So Shores are known for the algorithm, but Shore has designed the sequential way how to solve these things. But before that, before it is being called a Shore's algorithm, it's a purely a mathematical problem what Shore has faced. Because um, until this slide, you can also be sure that it is a mathematical problem, right? See, it's a mathematical problem. There is no there is a no pattern, so it's a pure hardcore mathematical problem. Yes, it's a mathematical problem. Okay, these four methods are there, but it is not the fastest method. We have to find the fast method. So what the show did, the show has not designed the algorithm. He rather designing the algorithm, he has found a shortcut method. Okay, and that shortcut method he has found in such a way it is very useful in the for the quantum Turing machine. Okay, so let's discuss this method. So what Shore has found, the Shore has found that he is saying that do not search the factors. Okay, he has converted this factorization problem. Okay, he has converted this factorization problem to the periodic problem. Okay, he said that don't search the factors, search the period of a function. A special, why I write the special, I will tell you. Uh, the thing behind this is special. There will be a 10 minutes more I will take to define this speciality of the function. So what the Shore has said that just don't go on the factorization conventional method. Just find the periodicity of the function. Okay, and that function should be a special function. The special periodic function. So what is a special periodic function? It should be, yeah, it's a name written there. Yeah, this is special function. What is this special function? So what is this special function? First specialty is that it's periodicity. Okay. So take one function fx, okay? Take one function fx which will have the periodicity, which will have a periodicity. A periodicity, what is the meaning of periodicity? Periodicity means it repeats, yes, itself after certain time. Yes, this is periodicity. So we can search for the periodicity. If we will tell this to the students, they will say that periodic functions are more lot more. So yes, there are a lot more periodic functions. When you will search for the periodic functions, sine functions are periodic function. Cos functions are also the periodic function. This is a sine function. This is a cos function, periodic function. Okay. Then you can find a square wave. Yes, it is also a periodic function. After a certain level term, repeats itself. In fact, any type of wave which repeats itself, you can say the periodic function, right? Which follows the periodic motion, which follows the simple harmonic motion, oscillation. If it's physical system, if you want to find, then oscillation, it follows the periodicity, right? So there are a lot of mathematical functions, there are a lot of physical things which follows the periodicity. So every function can work at here. So the answer is no, not the every function will work here. Okay. So then what will work here? What is the second thing? So first thing is that it should have the periodicity. Okay. So suppose I'm taking a general function of the form of the function fx, and periodicity means we know that for every x there will be a value for fx. So if we plot a table, so for every x there will be a mapping in fx. For every x value of x there will be f value of fx. For every x, there will be value of fx depending upon what is the function. Is it e ki power something, e ki power something plus log, or e ki power something plus sin s plus log? Depending upon that, it will have the value. Yes. Okay. Now you are taking x is equal to 1, x is equal to 2, x is equal to 3, like that. Suppose at x is equal to 4, the function fx value, suppose at 1, the function value is 3. Not 3, if I suppose I'm taking 11, suppose fx value is 11. F2 will be something else. It will be something else. But suppose at x is equal to 4, again, this value of function repeats to the 11. So this is the mathematical way of representing. This is the physical way of representing in the wave method. Okay. So this I'm telling you. So in either way, you can understand this periodicity. Okay. So this is the graphical way. Okay, physical way. Now this is a mathematical way. So at x is equal to 4, the value repeats. So then we can say this is the periodicity of the function. Right? Yes. So Shore said that we have to find the periodicity of the function rather than the factor. Don't go on the factor. Okay. So the periodicity of function. Now every function will not work here. Okay. So what the other another requirement? First is periodicity. The second requirement is that that periodicity. So suppose we are terming that periodicity as R. So at here we are terming that periodicity suppose R. So that periodicity, this periodicity should also depends on R. N. N is the N is the number which we want to factorize. Okay. So suppose N is the number, n is the number which we want to factorize, and we have to take some function which functions periodicity depends on n. This is the second requirement. Okay. So both the requirements are completed. What the Shore has found, it may be if we go in depth in mathematics, so there may be a more functions or composite functions you can form. Composite function means function fx1 into fx2, or you can say fx1 plus fx2, like that. Okay. Or you can say f1 f2 into f1 f2 plus f3 f4 like that. So all these are composite functions. So it may be possible, I am not ensuring you that it is only the function, but yet what Shore has suggested, what Shore has found, that this function is following all these two criteria. Okay. This function is following all these criteria. First this one, second this one. Okay. So uh, yes. So function is, that is, the function is a to the power x mod n. Mod n. Okay. So a to the power x mod n, what it means? Modulo function. It is called a modulo function. So what it means? It means this a to the power x, mod means you can divide. Mod means remainder of division. Okay. Mod means remainder of division. Okay. So a to the power x mod n means a to the power x divided by n, and then what will be the remainder? Okay. That is. So if we can form the function, function is this. What is the function? Function is fx a to the power x mod n. Mod n. Okay. Where n is the number which we want to factorize and x is the number. Oh, sorry, x is the sum variable. So now just see, for this, if we plot x, value of x and value of a to power x mod n. So we have to take one example for this. So let's say example we are taking for a 35. We know 35 is equal to 5 into 3. Okay. Example we are taking 35, 5 into 3. So at x is equal to 1, this is a. Yeah, there is one more thing. We have to take a. Let's choose a. There is a one more rule to choose a. I will tell you later. Suppose we are choosing a. For our convenience, we are choosing a is like a 2. Okay. So this is 2 to the power x mod n. N is 35 here. We are taking n 35. So let's take it. Let's clarify once again. Otherwise, all of you will be confused. What we are taking a problem like this. We have to factorize n is equal to 35. For that, we have to choose a function fx a to the power x mod n. For that, we have to choose a also. So there is a rule for the a also. A has to be GCD of this function, this number. Okay. So if the rule of a is GCD of n and 1. Okay. So for 35 and 2, so 35 and 1, the GCD I am taking 2. So that is I am taking a is equal to 2. Okay. So this is x is equal to 1. So 2 to the power 1. 2 to the power means 1 means 2 upon 35. Okay. So the remainder we will get 0 division. That means 35 remainder. When we are taking x is equal to 2, this is 2 to the power 2 is equal to 4 by 35. Even we are getting a 35 remainder. Okay. But x is equal to 3, this is 2 to the power. So until we are getting at here more than 36, 35, 36, 37 or 38, whatever. Okay. So then we can divide it greater than 35 at here. Then we can divide by 35. We will have some remainder at here. Okay. Then we will start to get the remainder. So with this method, we can find the remainder. We can find the remainder and we will find where this remainder starts to repeat. Suppose at x is equal to 11, 10, or suppose x is equal to 12, this remainder starts to repeat. I am remembering several times taken the example, that's why I am remembering. and for your side you can calculate, right? So suppose x is equal to 12, this periodicity begins, this value begins to repeat itself. Okay, so when this value repeats itself, then we can choose this is the periodicity. So this is this value will we choose periodicity. Periodicity means r is equal to 12. That means because r is small r, we have taken a periodicity, right? So this. So when r is equal to 12, 12 is the periodicity coming here. Okay. Now, hmm, yes. So then in from this method, we can find the periodicity R, right? We can find the periodicity. Now, after finding the periodicity, so if all of you are teaching this Schwartz algorithm, then I'm actually I'm not fully elaborating all these things. I'm just elaborating where the question of why was coming while in teaching. Okay. So that means I'm just reconnecting the points I also told you. So when we are teaching, we are finding some difficulties that suppose a periodicity has come there. Okay. So this periodicity has coming to us. Okay. So after this periodicity, we are doing a Fourier transform for this. We are doing a Fourier transform for this. Then now I'm going to tell you why this Fourier transform is important. Okay. So the function is periodic, but there is a certain problem in it. Okay. So what the certain problem is? So when because we have to apply all these things, why we are finding the periodicity, I will also tell you, because we have to apply these things in the quantum Turing machine, or we can say after hardware has come, then it is converted into the circuit model, or you can say we have to apply in the circuit model. Then we have to say we have to apply these problem to the quantum computation, quantum computers. Okay, quantum computer. Now, so with this aim keeping in mind, we have to apply the quantum computation. And for quantum computation, the key is superposition. This is the first key. Second key is after superposition, there is a phase. When we are going to read it, it's a phase estimation. We have to read it. Then after that, measurement. We have to take a measurement. These are the three things. Okay. So in the quantum computation, we have to make the superposition. Okay. And this is where this superposition, this is where the difference lies between classical and computation. Quantum, sorry. Okay. How these things are, as I described yesterday, there's one example, vegetables example. So in one shot, if there are 100 vegetables, if there are 100 vegetables, so in one shot, we are measuring this vegetable constant or not. Okay, in one shot, we are measuring this, what is salty, what is sugar, who is sugary, who is having a sugar in it. So this is our beauty of the quantum, that in one shot we can take the inputs. So in a one spoon, we can, in a one spoon, in a one shot, we can take all of these things in a one step. This is the beauty of the quantum. Okay. So whether it is 100 or whether it is 1,000, whatever, or 10,000, we can take in one shot. Okay. This is the difference between classical and quantum. Okay. See, this difference I'm telling you, you can search out, you can go through the books. This difference is the real difference between the classical and quantum. Otherwise, all things will be same, will remain the same. Okay, all things will remain the same. So this is the difference. Okay, so and this difference makes very valuable technology in this world, this quantum. Because from this you can see that it increases the speed by 1000 factors. It increases if there is a 10,000 inputs, they are taking all the 10,000 inputs in a one time, all the 10 times input in one time. So that means it increases the speed 10,000 times. So it depends, whatever inputs you are having, it increases the speed as much as times. Okay, because of this beauty of the quantum computation. Okay, so the beauty of the quantum computation, again I am emphasizing, is to take in a one shot all the inputs. That is called parallelism. And this beauty is called quantum parallelism. Okay, this beauty is called quantum parallelism. I'm not writing, I was just symbolizing the few things. Quantum parallelism. Okay, and why this quantum parallelism? Because of the superposition principle. Why we can take in a one shot? Because we are able to make it superposition. Because all these things are the object for us for the mathematical point of view, and all objects have the vector, and vectors we are defining in the operators matrices, and when we are defining operators, we can have the superposition of these vectors or superposition of these operators matrices. Okay, so that's why we are able to superimpose all the things in a one shot. Okay, so this is real beauty. Oh, everything is a, you can say it's a mathematical, it's a physical, but this is the real beauty of the quantum computation also. Okay. So, yes, what I was telling you. So just like in a one shot, now just see the beauty that classically, what is the benefit? Now, what is the benefit to convert the problem of factorizing problem to periodic problem? This is the real hurt. Okay. Rest everything you can see, but this is the real hurt. Why we are converting factorization into a periodic function? Because periodicity enables us this type of inputs. It enables us the inputs. Yeah, we don't know the inputs, but it enables us as equal to 2, 3, 4 like that. Is enable to put all these type of inputs in a one shot. So when all these type of inputs we can superimpose in a one shot, then it means here the speed lies. Here it enhances the speed and take off the plane. So when we are converting factorizing problem to a periodic problem, so this will be like this. Okay. So all these inputs, x equal to 1, 2, 3, 4, what we want to find the problem. So all these inputs, if there is x is equal to 150 till that, one say 150 from 1 to 150, right? All these figures we can input in a one shot and we can see the periodicity. And when we came out for the periodicity, then the problem is the left hand game, no problem. Okay. Then rest of the things, it can also be converted by, achieved by classical computation. But this thing, we require the quantum computation. Okay. So this is the beauty. Classically, we have to input one by one. One by one. Because in the factor, we have to input one by one. But in the, because we have converted this factorization problem in the periodic problem, then all these things to find out the periodicity are, we can input in a one shot. Okay. So now coming to the next step, that we have covered, we have evaluated the periodicity. Okay. So the periodicity, if we have evaluated, then now the next problem will come. Okay. From the quantum computation, from the beauty of the quantum computation, we have enabled us to input all the things in a one shot and are successfully achieving the periodicity in a one shot. So in a one step, we are achieving the periodicity. But what will happen then? Next. Then next drawback of the quantum computing. Now coming to the drawback of the quantum computing. So the drawback of the quantum computing is that whenever we want to measure some system, we want to measure something, then in the quantum computation, if we want to measure something, then we have to disturb the system. This is first drawback. And secondly, when we are measuring, then among all these shots, among all these things, all only one value will come at the measurement. We have discussed a lot in the initial sessions of the FDP that after measurement, it will become a classical. That is, it will give you one value. Okay. Now, this one value is the problem for us. Okay. This one value will be a problem for us. Why? Why? I'm telling you why. Because periodicity. Okay. So in the superposition, when we are getting a superposition of all the 100 inputs and we are finding the periodicity, but if we are finding the periodicity, then this periodicity is running in dreams. The superposition is just like a dreams. We have discussed a lot, right? So this periodicity is in the dreams. It is in the air until unless it is being measured. And for the measurement of the periodicity, for the measurement of the periodicity, suppose function value of fx is coming like this: 3, 5, 7, 9, 8, and then again 5, 7, like that. Okay, 9, 8. So if suppose initial 3 values or initial 4 values are coming, we are not able to define the periodicity. If initial 5 values are coming, we are not able to define the periodicity. Until unless periodicity we will define until unless we are able to measure the things values until this point. Then we are able to see that yeah, 5 is coming at here and 5 is coming after the fourth step. Okay, this will come and again this will come. So if we are not measuring until this point, if we are measuring until this point, we cannot say the periodicity is 5, 7 or 9, whatever. Okay, we are not able to say this. So we are only able to see the periodicity if periodicity the quantum computation is finding. Okay, that's no worry. So we have to design an oracle or a function for that. Okay, circuit for that oracle, that is a to power x, a to power x model. We have to design a circuit for this. But this circuit designing we can do in the classical also, we can do in the quantum also. Okay. But the main problem is this: after the circuit design, when the circuit executes, then when we want to measure quantum mechanically, so quantum will give you only a one value. Suppose we are measuring, it will give you this value, it will fix this value. Then from the one value, we cannot measure the periodicity. Okay, so this is the real problem. So we want to measure the periodicity. That's why we want at least these multiple values, 4 or 5 values. But measurement will give you one value only. Among the superposition principle, it will fix a one value only. Okay, this is the problem for us. To remove this problem, what we are using? We are using a QFT. Okay. So these things are based on my personal experiences. Okay. So these things are I found in majority of the faculties. Don't mind, but I found majority of the faculties that they are not knowing that why this quantum Fourier transform is being used at there. Okay, to find the next level things. So student may ask that what is the problem in converting in the periodicity R. Okay, so this is the problem. So until unless we are applying a Fourier transform, now what will happen to the Fourier transform? See here, what will happen to the Fourier transform? Now, Fourier transform, we know it is very much used. Fourier transform, it is a mathematical tool. It is very much used in ECs, electronic and communication, inverse Fourier transform, Laplace transform, all this transformation. Transformation means, because these are the transformation. That is, transformation means it changes one system to another system, one to second. And system means actually it is going to change the basis of the calculation. basis of the calculation. Or if we are dealing in the graph, then if this graph is based on x, then in the other system we can change this graph based on t. Okay, we can base this graph based on t. Okay, so this is the work of the Fourier transform or Laplace transform. All these transformation are working like that to changes the basis parameter. Okay. All of now actually I am working from the hardware side. So in the hardware, unless it is being known, you cannot design your root things. Okay. So this conversion from x to t, this conversion from one basis to another. Okay. We have taken the Shore. So yeah, not we. Shore has taken the advantage of this conversion. So what they did, if we are able to convert the periodicity, this is the periodicity value of x, right? Or r, we can say. So this is multiple values of x, x1. Okay, we will draw once again. Suppose graphically all these values are coming, and suppose this is a value of x1, this is a value of x2, this is the value of x3. Okay, this is the value of x4, this is the value of x6, 5, 6, like that. Then if we are going to measure this thing as it is, this is the value of x1, x2, x3, that is periodicity r, it is going. If we are measuring simultaneously 4 or 5 values, then we can observe what values are repeating, then we can say the periodicity, find the periodicity. But the problem is that the quantum mechanical measurement give us only one value. Suppose we are going to measure, it will fix this value. Then from this value, we cannot say that what is the periodicity. Okay. So to remove this problem, it is converted into the, from this x, it is converted into the frequency domain. Frequency domain. Okay. We know that transformation, Laplace, Fourier, all these transformation are used to convert the basis. So now this basis we are converting for the frequency domain. Okay. Then when we are converting this into the frequency domain, then here frequencies are f1, f2, f3, like that. Then now just convert to the frequency domain. Now you apply the quantum measurement. This is the quantum measurement. When will you apply the quantum measurement? Then it is very much easy to fix. Suppose it is fixing this value, because quantum measurement is fixing one value, that is f2. Then it means we are left with the function, frequency f2, right? And we know that frequency is a position of the time period. This is a time period, right? Time period. If I will write capital T, yeah, there is a definite formula. Everybody knows 1 upon T. But you may be mistaken by this. This T is not the time. This T is actually the time period. Okay. This T is actually the time period. So if we are knowing the frequency from this after converting into the Fourier transform, then Fourier transform means converting into the frequency domain. Then we are measuring, then it will fix a one frequency. That frequency will give us the time period. And this time period will be the direct measure of R, because R is the periodicity. Periodicity means period, after which time period denotes after which time the wave repeat. And the same we want to scratch out from this, right? So this is the periodicity. We can find out the periodicity from this method. Okay. Until now, we have find out the periodicity. So the quantum Fourier transform, we have find out the periodicity. Now we can give the, when we are finding the periodicity, now we can give the again measurement to make it to the final output. Okay. For the oracle. So that is how now if we want to design a circuit, we can say is, so schematically we can say the circuit will be like this. So first we want to use the superposition for inputting all the things, all the inputs, right? Then after superposition, after inputting, what will be done? It will be processed through some formula. That formula here is a to the power x mod n. This is the formula. And this formula is hidden in the oracle. Oracle. Okay. We are calling this oracle as a black box. Okay. We know, designer know this formula, but others will not know this formula. Okay. So means customers. So after this process, what will happen? You will left with the periodicity, but how to measure that? Because we are left with the periodicity, it will give you the periodicity, but in air or in dreams, right? It's a airy periodicity. To convert this periodicity in the measurement form, we have to take a Fourier transform. That is called quantum Fourier transform. Okay. And after the quantum Fourier transform, we have to do the measurement. Okay. So this will be a certain circuit for that. Now, for the superposition, we know that 0 convert to the superposition state, 0 plus 1 by root 2, right? For the superposition, we need a Hadamard gate, and that is converted by the Hadamard gate. Okay, so we need a Hadamard gates. Hadamard gates in parallel, because as much as inputs, as much as Hadamard gate will required. So what will be the sequential circuit? The Hadamard gate is required. The Hadamard gate is required. Suppose there are 4 inputs, the 4 Hadamard gates are required at here. Okay. Then after this Hadamard gates, all of the 4 Hadamard gates, there will be oracle. Oracle. And after this oracle, there will be a QFT. After this QFT, there will be arrangement for the measurement, or we can form this line. Okay. Then we will get a result. So overall, from this method, this is the beauty of the quantum. It starts with this beauty. Then this beauty, this is the drawback. To remove this drawback, this is the drawback of the quantum, that measurement will give us only one result. But we want the multiple result to sketch out the periodicity. Okay. So this is the weakness. And to overcome this weakness, we have used the quantum Fourier transform at here. Okay. So this quantum Fourier transform, after this, we can measuring. Okay. So that is for the Shor's algorithm side. Okay. So I hope so. I am able to make a clear every point, every step in this algorithm. I have not gone in the conventional manner. I have gone, as I know that all of you are faculties. So I have gone that at what point the students are facing, a student may face the problem. You can deal with the students from this scenario. So, okay, let's move ahead. No, this we want to clear. Yes. So, these are the certain things. Yeah. Steps: apply the Fourier transformation, that x-axis to frequency axis, and that frequency now gives a random x. Okay. So now coming to the hardware side. Before coming to the hardware side, let's quickly do one Qiskit uh, demonstration of this algorithm. Uh, okay, let's do a Deuce algorithm demonstration. For that, just I want a half-minute break to set up my Jupyter Lab. Hmm. Jupiter. New. Hmm. We can now share. Hmm. Zoom. Yes. Yes. So here is Jupyter Lab. Just so what I said earlier, we have to import the quantum circuit. So importing the quantum circuit. Hmm. Then we want to import the simulator. We can do this. Then now again, one more, yeah, histogram. So just take visualization and histogram, import, and let's run this at the backend, right? So let this ready. So we are writing a program, then it means what? Suppose in this we are programming a deuce, so we have to write a program for the oracle also. So first we are taking oracle and that as a constant, and in the bracket we was taking a qubit name is QC, and then returning to the QC, and then we will use it QC, just return. Then again we can say defining a constant 1, because in the deuce we have to define the constant inside the constant there may be a 0 and 1. Oh, the screen sharing is forced. Why the screen sharing is paused? Yeah. So so now we are defining and constant 1 also, right? And then we have to define both the 0 and 1, 0 and 1. Then returning, I think everybody will know. Yeah, there is a syntax. So yeah, the space between them is remaining. So minute. We have to close this one. So yes. So yeah, the line is present. I think everybody knows in the Python, if this is number is coming, it means we have learned the right command. So now we have to another label. So we can write it like a deuce or something else. So now we will define this QC, the quantum circuit with the values and taking place the high Hadamard gate. So this is the Hadamard gate I'm placing. And now we know that constant, and we have to run this also. So this was running, plotting the histogram. So you just see that we were checking for the both the inputs whether, see, defining first 0, then 1. After that, we are defining a balance condition. Then if oracle is balanced, and this will be the gates. Then in the another programming, we have to also define if constant is 0, constant is 1, balanced and not. Then we have to apply the, in the same programming, we have to apply the Hadamard gate for the quantum superposition. And finally, we have to run this for 1000 times or 500 times. You can do this and take the result. The result is, so it's a 0. 0 means constant. Constant means that is 100 times, 1000 times we have run and we have got a result 0. So it is only the simulator. Again, I'm saying, so you can only roughly estimate whether your program is working or not, but the real hardware, we can go on IBM or Google Sera. Okay. And suppose for all other results, if we want to check, then we can check by writing C. Now we have checked for the one result that is also coming 1000 times. So the histogram is very used, a full tool to check whether they are right or wrong. So I always suggest you can use the histogram initially. After a certain level of expertise, you can skip this step in it. So this is some sort of demo how the Deuce programming is working. So it's nothing else in the Qiskit, only you have to know the Python programming. That's it. So there is import, you can import all. 1 minute. Yes. Yes. Okay. So let's move towards the hardware side. So we were saying that, yeah, there is a lot more things. So in the hardware side, as we know that all these things are wasteless, all these things are airy, all these things are like a dreamy things if hardware is not there. Okay. I will tell you one example for that. Suppose we are writing. Suppose I am writing a letter at here. Okay. So in the initial session, I was asking about you this. I was saying that the when we there will be a lot of density in the room. When lot of density, 100 people are there in the room, then it will be a malfunctioning. So malfunctioning will be in the change of state. It is possible to stand at the same place by compressing yourself. Okay, it is possible, but it is not possible exactly rightly change your place or exactly rightly do the exercise, right? It is not possible. So change of state means, because quantum is always going on the time evolution, change of state from one to state two, right? So it is not possible to change the state. If you are making this state change, then it will be possible to disturb the others. 100% compulsory, you will disturb the others. So like that, if I am writing a from now coming from the hardware side, if I am writing a, then this a writing instruction is going to the compiler, right? And this compiler is making these instructions to the hardware. This software instructions going to the compiler making the hardware instructions. Then it is going to the hardware side, that it is going to the hardware side that hardware means, all the logic gates. Hardware means logic gate, and logic gates recognize 0 1. So there is a binary coding, there is a hexadecimal coding, and like that. So that this coding, suppose I'm saying from which bus, from which side of the IC it is going. So suppose I'm saying that is this code is written 000111000110. Suppose this codes were written in the previous state when the computer was on. Okay. So this portion of the IC has at it this code. Whatever with the string, you can say 01110. In the registry, you can say find out the strings are there. So in the classical computers. So suppose this code is written. Now, if I am saying write A, and A code is having a instruction 1001101001. Suppose this code compiler has coded in this instruction of forming a, right? Then when your computer is in this state 1, he has to go on this stage 2. Okay. And we know that in this portion of IC, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 transistors or 10 diodes which are flowing the current. Now, 0 means we know, 0 means off, 1 means on. So this code is like that: off, then on, then on, then on. This transistor is also off. This is an off state. This is an off state. On, off state, like that. Now we have to change the state. Now to change the state, what? The transistor which was in off state previously. I should take another color. Yeah, the transistor which was at off state previously, it has to be on because the code is 1. It has to be on, right? So to on, it has to flow the current in itself. So there is a change of state. Here the current code is 0. Previously it was in on state. Second transistor is in the on state. Now to comply this code A, okay, at the output, we have to off this transistor. This transistor we want to off, right? Like that. This is 0. Again, this transistor want to off, this transistor want to on, like that. Okay. So we will follow this code 10011010001. Off, sorry, on, off, then on, like that. So that means what I mean to say from this example, what I want to convey, that on to off state, there is a toggling. This is called toggle, a toggling state. We have to go to the toggling state from state 1 to state 2. Several togglings of the transistors or diodes is required. Yes, somebody has raised their hand. The toggling is required, and this toggling is called the change of state. So because we are going at the lower and lower size, so change of state is not possible. If it is possible, then it is possible, it may be possible, because these are very compact, situationally placed, right? Now as we are going to the nano level, this compaction is so much less, that if it is going on the on state, so while going on the on state, it may disturb the state of this. It has to be on the off state, but may be possible because of this influence, it will malfunctioning, it will go on the on state. So that means whole of the coding will get disturbed, or maybe possible, instead of 100, instead of it will code like this 11111 00011 like this. When it will code like this, then your output, maybe it will be a code of another output. So maybe that code will be of this output, only of this. So you are giving the instruction to type A. Coding is this one. But because of the lesser size, it has malfunctioning, improper coding, improper disturbances, and because of disturbances, several another code, another word or letter has been displaced. A symbol has been displaced at here. So this is called malfunctioning. So as we will go in the lower size, the malfunctioning will occur 100%. Okay. So this is the hardware perspective. So now from this perspective, I will talk about some parameter we have to change as we are going into the quantum size. So we have to change this parameter. Okay. So now we are coming on to the parameter. I think this is really clear to you from the hardware side. Yes. Now, so in the classical computers, the parameter is, we are taking a hardware like diode, we are taking a hardware like transistors, and all these are running on a current. And we are making current as a parameter to denote the two states. The two basic states in the classical is 0 and 1. Okay. We are running a current. We are following a current, which is the physical parameter. Physical, which is the physical parameter. It's true, we are using a diode, we are using a transistors, on all these things are coming in the semiconductors. We are using semiconductors to make the ICs, right? But the from the what this semiconductor will do, it will follow the current to code the coding. Okay, this is the hardware side. Okay, so this current will have two state, either 0 and 1, depending upon if this is off. If the current is not flowing, we can donate off. If the current is flowing, we can donate on. And it is not necessarily here in the quantum hardware or in the hardware side, classical hardware, it is not necessary that 0 we will donate off, right? At somewhere on um, uh, some parts like in the drones or in the programmable ICs, what we are making in that ICs, what we are doing, it is not necessarily that 0 you have to take off. No. Suppose if the current is flowing 1 ampere, not 1 ampere is very much large. Suppose I'm taking current is flowing point, not point, suppose 5 milliampere. Current is flowing 5 milliampere. And in somewhere, the current is flowing zero point 0.5 milliampere. Suppose. Okay. Then we can make this as a parameter for 1. We can code. This is only the matter of coding while designing the ICs and designing the hardware. So we can code. We are doing a lot of manipulations at here in the hardware designing. Okay, I'm from the hardware side, so that's what I'm telling. Uh, so 5 milliampere we can code as a 1, and 0.5 milliampere we can code as a 0. Okay, So when the 5 milliampere will come in the circuit, it will recognize as a 1. When 0.5 milliampere will come in the circuit, it will recognize as 0. Okay. So from these codings, we can design our hardware also. So why I'm telling these things are also required in the quantum. So, but in the classical side, the current is the parameter. Okay, there is none other thing other than the current. Okay, we are making current as a parameter to code ourselves in the classical computing. Okay, so whatever software you are making, whatever the things you are making, all that software are going through the compiler, and compiler is converting it to the machinery language. And in the machinery language, it is they are machinery means diode, transistors, and ICs. So this compiler machinery language is giving the instructions in the form of codings, hexadecimal codings or binary coding like that. Okay, that coding, according to that instructions of coding, our hardwares are running. This is the real insight from the hardware from the classical side. Okay, now coming to the quantum side. Now just come to the quantum side. In the quantum, we know what is the basic difference. The basic difference in the quantum that there are in the classical, there are two states only. Okay, let me see. Okay, so yeah, in the classical side, there are two states only, 0 and 1. But in the quantum side, 0 state is also there, 1 state is also there, and mix of 0 and 1 is also there. Superposition state. We can call it superposition state. So the superposition state is also there. Sorry. So if any parameter we can catch it instead of current, because current only there is a 1 to 2 parameters. Okay. So we have to catch another parameter for this, for designing this 0 and 1 and superposition things. So that parameter on the very first side, the very first indication what maybe that parameter is that size, that classically we are at the macroscopic level, right? That's why we can find out macroscopical physical quantity, that is current. Okay, but quantum mechanically we are at the atomic level. We are at the atomic level. Okay. See, whatever things I'm beginning from the very beginning, from the very sketch. Okay. If somebody is missing the session, only then he is not able to understand. If he is not missing the session, then I hope the 100% of the density is going to absorb the things. So yes, so the quantum is from the atomic side, atomic level. And the atomic level, so we have to catch our parameter. Here the parameter is macroscopic level. Current is a macroscopic level. Okay. Because current is forming from the electrons. A lot of current is called, what the current is there. 1 minute. Let me remove these things. What the current is there. What the definition of the current? The definition of the current is flow of electron. Flow of electron. Okay. So that means it's not seeing the electron itself. Yeah, it is true. It is comprised of electrons. But this electronic property doesn't matter. Only the matter is the whole electron has to come here and not few of the electrons. Current is not the collection of few of the electrons. Current is the collection of million and billion of electrons that flowing in a flow of electron. This is called rate of flow actually. The current is the rate of flow of electron. Everybody knows, I think, current is Q upon T. Okay, charge over time. That is how many times in 1 second, 2 second, 5 second, what are the charges, number of charges flowing. Okay. So if 1 second, 10 charges are flowing, the current will be different. Okay. 10 charges are flowing, current is different. In 1 second, if 100 charges are flowing, the current is different. Okay. So the current is something that counts the number of electrons flowing per second. Okay. That counts the number of electrons flowing per second. So naturally, it is not seeing inside, it is not about seeing inside the electron. It is about seeing the number of electrons that is in the bulk. Okay, number of electrons that is in the bulk per second, and that we are saying a current. That means current is a macroscopic property, not the nanoscopic property. Okay, so for the classical computation, we are looking for one of the property which we can donate two states 0 and 1, that is off or on state. So either we can form a 0.5 ampere 0 or 1 ampere 1, like that. Okay, but here now come to the quantum mechanical side. So in the quantum mechanical side, what is required? In the quantum mechanical side, what is required? Quantum mechanics is for the atomic level, nano level size, right? So when it is from the nano level size, yes, when it is from the nano level size, we have to go for the atomic level. At the atomic level, when we go to the atomic level, so we have to follow the shape of the electron. We have to follow the spin of the electron. We have to take the atomic level properties. So atomic level properties, okay? Atomic means one atom, not the molecular. These are the microscopic. Current is the macroscopic property. But inside the microscopic, there is a molecular level property. Inside the molecule, there are atoms. We know that, right? So the property which is donating by atom, that we have to follow. So here, because quantum is a macroscopic, nanoscopic atomic properties, we have to follow. So we have to take atomic level properties, that is inside the atom. The electron is inside the atom. So electrons, the one property we can follow, its state of the electron going from clockwise or anti-clockwise, like that. This is one property we can follow. Okay. And this clockwise and anti-clockwise, we can donate 0 and 1. Okay. So we can follow this property. Then this is called spin, clockwise or anti-clockwise. Then we know that there is a one more effect of the electron. Maybe any hardware side or electronic engineer may know that inside the atom, whenever the atom is placed in the magnetic field, when the atom is placed in the magnetic field, then this clockwise or anti-clockwise labels are also are clockwise, and anti-clockwise spins are also this level. Firstly, these levels are called energy level. For this is the one energy level, this is the two energy level, right? But when this atom is placed in the magnetic field, this 1 and 2, these energy levels also is split in several energy levels, is also split at several energy levels. Okay. So this clockwise, this anti-clockwise. So see here the difference in the classically, we are forming a property which depends on million or billion of electrons. Million of electrons. Okay. Then million of electron is forming a one current, and we are having a different ICs, different currents. Then there is a different, we can say different million of electrons. But at here, and that different million of electrons, we are denoting only two states, 0 and 1. See the difference. But at here, in the quantum mechanical, we are, if we can form this parameter. What parameter? This electron spin. Then one electron, there is a million and billion of electrons is forming these things, current, and that current is at the different ICs. So at the different ICs, there are million of electrons at here, there are million of electrons at here, million of electrons at here. If there are 100 sites, there are 100 million of electrons that denoting the current, okay, a property, that denoting 0 and 1. Two things. Now come here. Now we are talking of the one electron. So to the one, only one electron can give us, there are million or billion of electrons. Here is a one electron that is giving us two states, 0 and 1. And if we will further place this in a magnetic field, then the further only the electron having a two states, then further these two states divide into the multiple states. You can see this difference. So space complexity accommodate very shortly in the quantum. This is the first scenario from the hardware side. Okay. So here million of electrons are accompanying only 0 and 1. Million and billion of electrons. Now there is one electron that is accompanying a several stages. It can code in itself. Only one electron can code, have the code 0, have the code 1, have the code of superposition state in this. At the code of superposition states in this. Among various, these are various superposition states we can form the parameter. Okay. So that is basic for quantum and classical difference at what level. So we can say that here only one electron can form several superposition states also, or several, okay, several superposition states. Now you can say that, yeah, that means only 5 electrons are sufficient to carry the data of all the classical computers. I can say yes. If you are not believing, you can increase the only 100 electrons. 100 electron is nothing. It's nothing. Okay. So 100 electrons can carry the all over the world data of classical computers, whatever in the clouds, whatever the things. Okay. Yes, because they have the so much several states. These several states are superposition. But you can you can say that I'm talking in this way that the quantum will finish everything. It's a big dragon, but there is a certain physical level restrictions. Theoretically, we can say that yeah, it's a big dragon, but there is a certain theoretical restrictions. The theoretical restrictions is that uh, theoretical restrictions are this that yes, it is when this atom is placed in the magnetic field, it is divided into the several superposition states or several levels. These several levels we can define superposition states. But what is the guarantee we can see these superposition states? Okay, this is the restriction. How how we can see these superposition states? Because we want to open this rack. Now this is just like a rack where we want to place our luggage. So to open this, we required first atomic level access. Okay. Where are the racks? Racks are inside the atom. Racks are inside the one electron. Can you touch? Can you see the electrons? No. Can you touch the electron? No. So how can you access this electrons? Only one electron or 5 or 10 electrons. You cannot access. Okay. But now I'm saying on the deeper level, when these electronic states 1 and 2 clock and anti-clockwise states are dividing into several states, you have to access that also. So it is just like that. This is a bigger rack. Inside this there is a very small rack, and inside this there are hundred of smaller racks. Can you access these racks? No. Okay. So you cannot access that racks. Okay. So that is the physical restriction. And because of this physical restriction, everywhere in the company, whether it is a IBM, it is a Google, or it is there are several startups are there, they are restricting themselves. Okay. So to access, to go in the these very fine level, you are required a very fine level of treatment scientifically, very fine level of treatment from the material side, from the hardware side. So much fine level of treatment requires costly instruments, requires the costly things. Okay. So, so this is the very fundamental basic thing I am telling you from the hardware side. This is the classical and quantum restrictions. Okay. So now these things are break. I'm saying these things are break. Okay. Let's clear some of the things. It's going on so much meshy. Okay. Now, So, yes, first thing is that this magnetic field we are applying, and if we are catching, we can have the axis of these racks, okay, or almiras, then we can store the information. And but the our physics is like this, okay, science is like this. It is not giving us so much access, okay. For anyhow, if we are accessing for the 1 second or 2 second, then it will not work for us. If we are giving the access of 1 hour, it will also not work for us. You know why? Suppose you have kept it is access for the 5 minutes. Suppose I'm telling it is access, it is giving you access for the 5 minutes from the high level instruments, and you have kept your luggage inside this. You have kept your data inside it. Now it is closed. But then again, when you want to read it, you have to open this. Again, you require so much of complexities. So that complexity is one of the level. I'm coming to the next slide. One of the qubit. So this is this we want to represent as a qubit. All these things we want to represent as a qubit. So one of the qubit is a superconducting qubit. Superconducting qubit. So in superconducting qubit, that qubit is access at minus 250 degrees Celsius. So at so much low temperature, it has the access. So this racks you can access at this much of temperature, and it's not a joke to go at this stable temperature. If I am wrong, suppose some more technology may come that can go up to minus 234, 230 degrees Celsius. Okay. So minus this because the superconductivity can achieve at 250, minus 250 or minus 230 like that. Okay. So so these are the very complexity ones. So to achieve this so much low temperature, to run the superconducting qubits, so much low temperature we required. So much low temperature is involving so much complexity, so much cost. Okay, and so much of hardware space is required. And this is the thing. And along with this, you have to apply the magnetic field. You have to apply the magnetic field like this. Then you can have the dividation of the almiras, right? So these are all these things are very complicated. So you can generally you are seeing the image of very complicated ones in the quantum computer, like images are like that. There are several stages, and there's coming like this. Okay. So all these things are very complicated. So the quantum computation is very costly, very costly, very costly. Okay. So now, with this, now I'm coming to quickly. Time is very low, so I'm coming quickly to the several. 1 minute. Yes, several level of our qubits. So there are several level of qubits. So superconducting qubits are there. Okay, the trapped ion qubits, photonic qubits, neutral atom qubit. Neutral atom means there is no ions, there is no charge. Silicon spin qubits and topological qubits. The latest technology is running on the topological qubits. Okay, so all this time is less, so I'm unable to describe all of these things, but I will provide all these PPTs to you that what are under the superconducting qubits. Superconducting, I told you that we have to go for the very less. And yes, in all of the qubit, we need to remind, or in all of the qubit, we need to remind that there must be a provision to accommodate this state and to accommodate one state. And also we it should have all type of qubits should have the provision to accommodate the superposition. Okay. So, based on this, we can have a larger and larger. 1 minute. It's not. Yes. So, now coming to the, yeah. So these are the latest things. So IBM has made five. They have started from the 5 qubit, but now they have reached on the 1,000 qubits. So the superconducting qubits are also classified on the three type of qubits: phase qubit, transverse qubit. Okay, and these transverse qubits, the IBM are working. Even the Google are also working on these transverse qubits of the superconducting. Okay, so superconducting is also having these. 1 minute. Yeah. Phase qubit, flux qubit, transverse qubits. Okay. So among these three, the transverse qubit is the very advanced coming in 2007. So in 2002, the phase qubit was there. In 2005, flux qubit was there. But the transverse qubit is the latest qubit technology. 2007 it has been come. And from now, IBM and Google and all these are using this transverse architecture. Okay. So latest development is that IBM has developed in 2023. He has developed a 433 qubit quantum computer from 1,000 qubit computer. It is they have launched recently 2023. I think January 2024 they have launched. Okay, that processor they have launched. Google is also simultaneously working on the synchromon processor, but its accessing of the qubit is very low. So it has reached from the my latest knowledge is that you can search on the net for the latest knowledge. You can go through the net, but my latest knowledge is that it can reach up to the 500 qubits. But it was known to have 100 qubit efficiency, but it has now declared that 500 qubits. Okay, and Google was the first one who has claimed that in 2019 they have claimed for the quantum supremacy. So the quantum supremacy means they have made the quantum superconductors, oh sorry, quantum computers, and at random circuit, this is called random circuits, random hardware they have made, a random circuit applying a X gate or Y gate like that, random circuit they have made, and they have run this random circuit in classical also and quantum also. So classically, it was supposed to take 10,000 years to run that circuit. Classical computer was supposed to run 10,000 years time. But quantum computer, Google has proved, they have claimed that this 10,000 years time from the quantum computer, they have reduced to the 200 seconds only. In the 200 seconds, the same work has been done. So Google has claimed that that is called quantum supremacy. So see there, the quantum supremacy was two times. Theoretically it was proved by Deuce in 1985 by designing quantum Turing machine and solving that algorithm. And then in the Google has proved this that he has claimed, but I think most of the peoples are not agreed, but most of the peoples are agreed. I don't know. So he has proved that 10,000 years program they have solved in the 200 seconds. Okay. So there are a lot of companies working on that. So this company is working on the ion trap. This company working on the superconducting multi-qubit. Then Psi Quantum, there is a startup also working on the photonic qubits. Okay. Then Zendo, yes, this is working on the photonic Gaussian bosons, and its projection is very big. It can win the race. I think these are the news that China has developed the quantum computation. Okay, so there is a race which country can develop the quantum computer first. They can solve the problems of the world problems very firstly, and then they can win the overall economic race where the US is dominating nowadays. So with this aim, the Indian government has also launched National Quantum Mission. All of your faculties are knowing you are getting funding by them. So you are writing the projects, getting the funding. Okay. So that's it from overall quantum computation faculty development program. So thanks for all. Now I'm open to the discussion. If you want anything, you can put your queries on the chat box. Hmm. Okay. So that's it. Thanks all of you for attending all these 5 sessions. So hand it over to Amma. So Hamas, can you take over? Ashita? So if any query, you can put on the chat box. So a lot of things.
Yeah, so dear faculty members, thank you so much for attending the FDP. So coming to the certification part, those who attended 60 and more than 60% of the session, they will be receiving the certificate within 8 to 15 working days to your registered mail ID. And about the upcoming program, so you will be receiving the information from our side via our official channels. So please stay tuned and we'll look forward for your active participation in upcoming programs. Thank you so much and have a nice day ahead.